Hello everyone. This is lecture number 3 on units and measurements. Let's start with the previous discussion only, which we ended in the last lecture. We will do some of the questions first, and then we can move on to the next discussion. I think the next discussion is based upon your combination of errors. Okay. So I'm Samir Lawankar. Let's begin our discussion. Okay. So first of all, the course outline for you. Okay. So we started with the introduction, as in what is basically units, right? Then the system of units were being explained. Okay. Then the system of units were being explained. Next thing was measurement of length. So basically, we understood generally for real surrounding things. What we generally use is we generally use the meter scale, then screw gauge, etc. And apart from them, we use things like, let's say, screw gauge or vernier caliper for some small distances. But what happens if we try to use it for very large distances? So then parallel method is being used. And if we need to use it same for the very small distances, then one way can be for the microscopy, which is the recent tunneling microscopy. And apart from that, one of the experiment or example we considered for the concentration of oleic acid, if we can by some means can make a monomolecular thickness of the substance we require, for which we need to find out the thickness of the molecule, or basically thickness of the oleic acid, and then thickness of the basically diameter of the molecule can be understood. Okay, so these all things are being understood. Range of lengths are being understood, and the next concept we understood the measurement of mass, in which we understood what is the basic SI unit of this, etc. Then next thing is measurement of time. Measurement time, we understood basically what is what is basically 1 second. Then different types of clocks will be understood, like cesium clock, etc. And then next thing is your finally in the last concept, we were understanding about your accuracy, precision of instruments, and errors in measurement. Okay, so we basically understood that what is errors and what is different things. Finally, there was a basic formulation type of thing which we understood, which was based upon your what is a mean, then what is percentage error, what is relative error, etc. So all these things were being considered, and then we were understanding these all concepts. And then finally, I think examples have to be understood, and then we can move on to the next concept. Okay, so let's not waste any time. Let's start directly from that concept only. Okay, so first next thing is let me start directly. Okay, let's start with this example here. Okay, so this example states that two clocks are being tested against a standard clock located in a national laboratory. Okay, so these are two clocks. Now we have to do some experiment. Just please understand the experiment once, and then we can go on. So at 12 o'clock noon by the standard clock, the readings for two clocks are this. Okay, so just refer to the readings once. So as you can see, there are two clocks here. This is clock 1, this is clock 2. Okay, now on Monday, the clock 1 was showing 12 hours and 5 seconds. Similarly, clock 2 was giving you 10 hours, 15 minutes, 6 seconds. And similarly, there are different times being given to you. Okay. Next thing is, if you are doing an experiment that requires precision time interval measurements, which of the two clocks will you prefer? So it's quite evident the clock which is having higher accuracy, we will try to use that thing, right? So let us look over the solution. So the range of variation of the 7 days of observation is 162 seconds for clock 1 and 31 seconds for clock 2. Right, so they are just trying to calculate the variation. What is the variation? So basically, when Monday at 12, so every time they calculated the value at 12 o'clock noon only. But as you can see, as the days keeps on passing, there was a variation being observed here, right? The range of variation observed was 162 seconds for clock 1 and 31 seconds for clock 2. Okay. The average reading of clock 1 is much closer to the standard time than the average reading of clock 2. Quite evident, as you can see that what is the average. When you will try to do the average reading of this, please be very clear, because the concepts of accuracy and precision both are to be used here, right? If I need to calculate time at 12 o'clock, then if my measurements are coming near to the 12, then we can say that it is more accurate, right? And if the amount of what we can say, the range of variation is very, very less, then we say that it is more precise. Okay. So these are just two concepts which I already explained in the previous lecture also. So basically what we understood is that the average reading of the clock 1 is much closer to the standard time. Quite evident, because as you can see all are approximately near 12 o'clock only. Then the average reading of clock 2. As you can see, this is around 10, 15, etc. Right? So the important point is that a clock zero error is not as significant for precision work as its variation. This is very, very important line, right? Because zero error can always be easily corrected, right? So what you just need to do, you will just add some minutes. Let's say I add around, if I'm not wrong, then it's around 1 hour, 44 minutes, and I think 54 seconds, if I'm correct. So if you will add this, then you will get exactly 12 o'clock, right? So if you keep on adding a constant amount, then as the precision of this clock 2 is higher than clock 1, why it is higher? As it is written here that the range of variation for the 7 days was lower for clock 2 and it was higher for clock 1, right? So that is only the evident part here. So just read the last line again. So the important point is that a clock zero error is not as significant for precision work as its variation, because a zero error can always be easily corrected. Hence, clock 2 is preferred to clock 1. So we won't add that plus value which I just wrote here, right? Which we will do the average of the all the times. What was the variation from 12 o'clock, and then we can add that average variation. Hence, we will be very, very closer to the 12 o'clock noon time. And hence, clock 2 should be preferred over clock 1. So that is our final conclusion from this example. Okay, let's move on then. Okay, so the next example states that we measure the period of oscillation of a simple pendulum. In successive measurements, the readings turn out to be 2.63 seconds, 2.56 seconds, 2.42 seconds, 2.71 seconds, and 2.80 seconds. Okay, so we have some 5 times given to you. These are the 5, I think 1, 2, 3, 4, 5. Yes, 5 seconds, 5 times are given to you. Calculate the absolute error, relative error, and percentage error. So it's nothing but just calculation part only. So I will just try to explain you everything which is written here. So first of all, the mean period of oscillation of the pendulum. So quite evident. First of all, you need to calculate the value of T mean. In the previous example also, I also explained you for the 4 observations. Let us do the same question for, let us do the same calculation for 5 observations. So basically, T mean will be nothing but equal to T1 plus T2 plus T3 plus T4 plus T5 divided by 5, right? So every value is given to you, just add up all these values divided by 5. So therefore this value which is obtained as 2.62 seconds is nothing but T. Fine. Next thing is, as the periods are measured to a resolution of 0.01 seconds. As you can see, why it is said that it is measured to 0.01 seconds, because there are 2 decimal places. Please look over to these issues very, very carefully, because the complete lecture series after this main part is complete, significant digits, etc. are being based upon the decimal places only. So please look over to this concept very carefully. Okay. So basically now till now what we got is that the resolution is just to 0.01 second, or we can say that the least count of the instrument which was used for the measurement of this time, or for the measurement of this period of oscillation was 0.01 seconds. Okay. So as the periods are measured to a resolution 0.01 seconds, all times are to the second decimal. Quite evident, as you can see, all decimal, all times are to the second decimal. So it is proper to put this mean period also to the second decimal. Okay, that's why actually the answer, when we divided 13.12 by 5, the actual answer came to be 2.624. But as the resolution of the device which we used for the calculation of period of oscillation was only up to 2 decimal places, therefore to capture that, or to be in the synchronicity of that concept or that device, we should also put the value of T mean to be 2.62 seconds only. Okay, fine, then let's move on. So it is proper to put this mean period also the second decimal. Okay, very small concept, just keep on understanding this and we can move on. So the errors in the measurements are, so now what are the errors in the measurements? Just give me one. Yes. So what are the errors in this measurement? First of all, so now what we are doing, we are just finding out, as in the previous concept, we were finding out the value of delta A. So what is this delta A? Delta is nothing but every value of AI minus the value of A mean. Right? So following the similar concept, what you will do here is delta T is nothing but equal to delta Ti minus, sorry, I'm really sorry. Delta T is nothing but equal to Ti minus T. Okay, so this is the concept only adopted here. So just keep on doing this. So therefore 2.63 minus 2.62 for the first part, then similarly your 2.56 and 2.62, and finally you will get, as you can see here, some values are plus, some values are minus. Okay, so these are just numerical things only, and calculation is being done here, nothing new here. Okay, fine then. So this thing has also been explained. Now next thing, let us move on to the next thing. Now what happens now? So final reason required is we need to first calculate the absolute error, then the relative error, and then the percentage error, right? So let's calculate the absolute error now. For calculating absolute error, you should know the value of delta T mean. So in the previous example, when we were understanding the formulas, what was delta A mean? Basically, delta A mean, let us say if I do for 4 examples, 4 observations, then it is delta A1 plus delta A2 plus delta A3 plus delta A4 divided by 4. Now, similar to this observation, what we can do is delta T mean is nothing but equal to delta T1 plus delta T2 plus delta T3 plus delta T4 divided by plus delta T5 divided by 5. Okay, so this is the thing which you need to do, and hence we will find out the value of delta T. Okay, so as you can see, note that the errors have the same units as the quantity we measured, the arithmetic mean of all the absolute errors. So first of all, we calculated the absolute errors. Those absolute errors are basically the values of your delta Ti's. So delta T1, delta T2, delta T3, etc. Right? Now delta T min is nothing but equal to addition. So basically we added upon all these values. Please remember, as you can see here carefully, please remember we are adding the magnitude values, right? We are not adding minus 0.06 here. As you can see, we are not adding minus 0.20 here. We're just adding plus 0.20 here. So that one thing has to be noted. Always delta T min is equal to mod of these values, right? So it's mod, and mod. Okay. So therefore delta T min is 0.11 seconds, right? Do please write the final answer of delta T min in the similar resolution only. In our case scenario here, it is two number of decimal places. Okay, so that thing is also been explained. Next thing is, that means the period of oscillation of the simple pendulum is, what is the period of oscillation? It's 2.62. What is 2.62 here? 2.62 is your T mean. As you can see, 2.62 is your T mean value. Therefore, just let me write it here. So it's nothing but T mean. And similarly, what is 0.11? 0.11 is delta T mean. Okay. What does it signify? What does it basically mean? It basically means that all the oscillations, all the period of oscillations lies between 2.62 plus 0.11 seconds and 2.62 minus 0.1 seconds. Or we can just add them and we can find that all the period of oscillations are lying between 2.73 and 2.51 seconds. Fine. Okay, so this thing is also explained. Next thing is, as the arithmetic mean of all the absolute error is 0.11 seconds, there is already an error in the 10th of a second. Quite evident, as you can see that there is an error. So they are just writing it. It's just theoretical portion that yes, there is an error there. Okay. Next thing is, hence there is no point in giving the period to 100. Okay, because as error is already happening till the 10th of a second, so there is no point in giving it up to 100. 100 as in 1 upon. So basically, the second resolution point is been explained here. Okay. Therefore, a more correct way to write this will be just reduce one error portion. Therefore, what we will get is, we can get it, or the correct way to write it is T is equal to 2.6 plus minus 0.1. Okay. So we have just removed one, what we can say, one fraction of the decimal. Okay. So that thing has been explained here. So because as the arithmetic mean of all the absolute error is 0.11 seconds, as you can see, it is already greater than 0.1. That's why there's already an error in tenth of a second. Tenth of a second, which that basically means that there is 0.1 second already error. So if you're trying to reduce that error, so hence there is no point in giving the period to 100. Okay. Therefore, a more correct way we will be rewrite t is equal to 2.6 plus minus 0.1. Okay. So just remove this two part also here from and one part from here also. Okay. Note that the last numeral 6 here is unreliable. Quite evident every time the last digit will always be unreliable. We will understand this concept more significantly in the what we can say in the subsequent slides on significant digits, etc. Since it may be anything between 5 and 7, we indicate this by saying that the measurement has two significant figures. Okay, so here two significant figures are basically this and this. Okay, let's move on with the further discussion. Okay, please you can for now you can just keep this as a theory portion only. We'll understand these two lines in much more depth in the subsequent slides. Okay, so why it is being talked about as significant digits, what is significant figures, etc., will be understood in much more clarity in the subsequent points. Okay, for now let us go ahead. Okay, so in this case the two significant figures are 2 which is reliable and 6 which is an error associated with it. Okay, so because it's 2.6, therefore it has two significant figures in which 2 is reliable. So I can just write here also so that a revision is also being taken place. So it's a reliable value and it's unreliable as in we can say that there is an uncertainty associated with it or there is some error associated with it, right? Okay, so in this case, the two significant figures are 2, which is reliable, and 6, which has an error associated with it. Okay, so for this example, the relative error or the percentage error is what nothing, delta A is equal to 0.1 upon 2.6 upon equal to 4%. What are these values? So as we calculate finally that the value is nothing but 2.6 plus minus 0.1, and as we know that delta A is nothing but equal to your delta A mean upon A mean, right? So this is your relative error, and if you need to calculate as percentage error, just multiply it by 100. So I think they multiplied by 100 here, and therefore they got the final value as equal to 0.1 upon 2.6, which is equal to 4% or 0.0. Okay, so I think that is the explanation of this example. So a basic point is, so one question can arise from this concept only, that there will be some values given to you and you have to calculate the absolute error, relative error, and percentage. Okay, so that being said, let's move on to the next concept here. Okay, so next concept is combination of errors. So in this concept, we will understand how, let us say there are two different quantities having, let us say they have the same units. Now we need to add those units. So if we add those units and both have some uncertainties associated with it, then how we will conquer the situation? How will we understand how to explain the answers related to it? How will we understand a total? Let us say there is some quantity z is equal to a plus b, in which a has some uncertainty, b has some uncertainty. Then what will be the total error or uncertainty in z value? This may be different in one's opinion, different in another opinion. What is the physical technique to do it, or what is the scientific technique to do it, will be understood in this complete concept subtopic. So we will understand addition of errors, subtraction of error, what happens when we try to subtract the quantities, etc. will be dealt. Okay, so let's not waste any time. Let's start the discussion directly only. Okay. So if we do an experiment involving several measurements, we must know how the errors in all the measurements combine. Okay, so that was only the crux which I just explained to you before starting this concept. For example, density is obtained by dividing mass by the volume of the substance. Quite evident, we know this. So density is basically mass by volume. So now one of the example can be understood is, let us say this mass has some uncertainty. Let's say it's m minus delta m, right? And similarly, volume has some uncertainty, v plus minus delta v. Then this density will have some uncertainty delta d. What will be this value of delta d is our final question to be understood in this complete concept. That what will be this value of delta d. Okay, let's understand. So density is obtained, so this thing has been explained. So density is obtained by dividing mass by the volume of the substance. If we have errors in the measurement of mass and of the size or dimensions, we must know what the error will be in the density of the substance. So the thing which I just explained you in the above part of this slide is just written here. Okay, so the final conclusion or final output of this concept is that we must know what is the error in the density of substance, right? So what will be the error in the density of the substance. So that is our main issue here. Okay. To make such estimates, we should learn how errors combine in various mathematical options. Operations, right? So let us start with the basic, that is addition. Okay. So first we will do for summation, then we will do for difference. So difference in minus. Okay. Let's start. So suppose there are two physical quantities. I'll try to go very slowly. I'm trying to understand this because after plus and minus, this may be very easy, but sometimes understanding multiplication and division will be quite tricky. Okay, everything is easy. Only just try to understand it slowly, and everything will be clear. Okay. So let's start. Suppose two physical quantities A and B have measured values. Okay, so as we say that every quantity which we are trying to measure always has uncertainty associated with it. Therefore, let us say that A has some uncertainty A plus minus delta A. Right. Similarly, B will also have some uncertainty B plus minus delta. Okay. So just let me iterate everything which is written here. So suppose there are two physical quantities A and B having measured values A plus minus delta A, B plus minus delta B respectively, where delta A and delta B are their absolute errors. Quite evident. We understood what is the value, what is absolute error basically. So if we know the true value of them, then A, which is measured value, minus the value which is true, gives you the value of delta A and delta B. Generally, absolute errors are magnitude-wise or positive values. Okay. When we write it as A plus minus delta A to understand that the measured value of A lies between A minus delta A to A plus delta. Okay. So that being said, let's move on. So we wish to find the error delta Z in the sum Z is equal to A plus B. So now let us, if we are doing this calculation in which Z is equal to A plus B, then we are trying to find out the addition. We are trying to find out the error, that is delta Z here. Okay. So now we have an addition Z plus minus delta Z. So now Z can be changed to Z plus minus delta Z. Okay. So now let's not look here. Let me just solve everything so that everything will be much more clearer. So as you can see, Z is nothing but equal to A plus B, right? Let us convert it into Z plus delta Z is equal to A plus delta A plus B plus delta B. Fine. So this thing is the concept here, right? Now we know that Z is equal to A plus B, so we can basically cancel these concept points here, and therefore finally what we get is that delta Z is nothing but equal to delta A plus delta. So that is the only thing which is written here. I think it gets rubbed when I close this session. Okay, fine. So there is no issue here. So that was the main concern, only two lines for being understood. So as you can see, we just added up here. So we can write as that Z plus minus delta Z is nothing but equal to A plus minus delta A plus B plus minus delta B. So now the maximum possible error. What is the maximum possible error? Okay, so let me just go back again. So let us say I write Z plus minus delta Z is equal to A plus minus delta A plus B plus minus delta B. Okay. Now here, as you know, Z is equal to A plus B, we can just cancel it. So therefore we will get plus minus delta Z is equal to plus minus delta A plus minus delta A. Right? Therefore the maximum value of this would be obtained only and only when we use this form, delta A plus delta A. That is my only explanation. Okay. So the maximum possible error in Z is nothing but delta Z, which is equal to delta A plus delta B. So similarly for the difference, what we will do? So it is same thing, only there is nothing to be explained, but I will go again here. So let us say we have Z is equal to A minus B was the concept we already know. So when there is error associated with it, we will write Z plus minus delta Z is nothing but equal to A plus minus delta A minus P plus minus delta B. Okay. Moving on. So this will be nothing but equal to Z plus minus delta Z is equal to A minus B plus minus delta A minus plus delta B. Okay, this z can cancel, so it is nothing but plus minus delta Z is equal to plus minus delta A minus plus delta B. So now out of this situation which is given here, what is the maximum error which can be obtained? Please look very carefully. The maximum error which can be obtained is again plus delta A plus delta B only. And hence that is the issue for that is the final output for your errors in sum and difference. Okay. Therefore, for the difference z is equal to a minus b, we have z plus minus delta z is equal to a plus minus delta a minus b plus minus delta b. And just do the calculations, and therefore finally you will get again that plus minus delta z is equal to plus minus delta a plus minus delta b. Therefore, the maximum error or the maximum value of the error delta z is again delta a plus delta b. Okay, fine. Hence the rule when two quantities are added or subtracted, please look over to this rule very, very carefully. So hence the rule that when two quantities are added or subtracted, the absolute error, so this is your absolute error here. Okay, so the absolute error in the final result is the sum of the absolute errors in the individual quantities. Okay, so that is the final crux which you obtain. Okay, so whether z is equal to a plus b or z is equal to a minus b. If both a and b have some uncertainties, then for both of these quantities we will have delta z is equal to delta a plus delta b. Fine. So first rule is being understood. Let's move on. Okay, to make such estimates, we should learn how errors combine in various mathematical operations. So we will try to understand this example, and then we can move with further topics or different concepts of this combination of errors. Okay. So the temperatures of two bodies measured by a thermometer are T1 is equal to 20 degrees Celsius plus minus 0.5 degrees Celsius, and T2 is equal to 50 degrees Celsius plus minus 0.5 degrees Celsius. We need to calculate the temperature difference and the error there is provided. Means basically when we try to find the difference in temperature, what will be the error associated with it. So basically we need to calculate the value also and the tolerance also. Okay. So simply T dash is nothing but T2 minus T1, as you can see. Therefore, it's nothing but 50 plus minus 0.5 minus 20 plus minus 0.5. Okay. Therefore, a subtraction of the value is always same. So it's a minus b only. So we'll do 50 minus 20, which will give you 30 degrees Celsius. But for the uncertainty portion, you won't give it as 0.5 minus 0.5, which is equal to 0. Here the uncertainty will be added up, and therefore this will be equal to 0.5 plus 0.5, which is equal to 1. Therefore, the uncertainty in the temperature difference calculation will be equal to 1 degree Celsius. That is the actual range in which the uncertainty can lie is basically 29 degrees Celsius, 21 degrees Celsius. Okay, so that was the basic concept of errors and sums and difference. Now let us move on to the next concept, that is errors of a product or quotient. Okay, so please look over very carefully, and then we can understand it at a much more deeper level. Okay, fine. So let's start. So suppose z is equal to ab, and the measured values of a and b are again a plus minus delta a and b plus minus delta b. Therefore, we can just write this in this form. Okay, so what is this form? I will just explain it here also. So as it is written that z is nothing but equal to a multiplied by b. So we can write z plus minus delta z is equal to a plus minus delta a multiplied by b plus minus delta b. Right? Left hand side is same. Just try to calculate the right hand side values. It's ab plus minus a delta b plus minus b delta a plus minus delta a delta b. Right? As you can see carefully here that the value that the value of this delta A, delta will be very, very small. In itself, when delta is small, that delta A, delta B will be very, very small as compared to all the concepts or all the thing which is written on the left hand side. Everything here written, right? Therefore, what we will do is first of all, let us understand this only. So it is just everything which is written here is being explained here. Now we are just finding out. So now it's mathematical formulation on how we try to calculate the value of delta z. So we divided the value of z here by LHS by z and here by AB, because as z is equal to AB, therefore z gets cancelled and it is 1. It's 1 plus minus delta z by z, and therefore this AB also get cancelled. For this AB, only one thing got cancelled. For this A, only this thing got cancelled, and its final thing is delta A, delta B upon AB. Okay, so using all these concepts here. So as it is written here, 1 also gets cancelled again. Now since delta A and delta B are small, we shall ignore their product, which I just explained to you of the black diagram, black slide, that delta A and delta B is very, very small. So we basically ignore this portion here. Okay, so we basically ignore this portion. Let's ignore it, and hence the maximum relative error. The final thing is we need to calculate the maximum relative error, right? So this maximum relative error. So this maximum relative error is nothing but equal to delta z by z, which is equal to delta A by A plus delta B by B. Okay. So how this thing came, I will try to understand, make you explain again. So z plus minus delta z is nothing but equal to AB plus delta AB plus B delta A plus minus delta A delta B. Let's divide this by z. Let's divide this by AB. So it will give you 1 plus minus delta z by z is equal to 1 plus minus delta A by A plus minus delta B by B, and we ignore those terms, so it's nothing but this. So it's delta z by z is nothing but equal to plus minus delta A by A plus minus delta B by B. If we need to find out the max value, max relative error value, finding out the max relative error value, it's nothing but equal to delta z by z is equal to delta A by A plus delta B by B. This is how this thing has been explained, right? So that is how this thing came here. So therefore, final conclusion of this is that when we are trying to find out the error of a product or a quotient, then delta z by z is nothing but equal to delta A by A plus delta B by B. Okay, and you can easily verify this, and this is true for division also. Okay, fine. So this thing has also been explained. Let's move on to the next concept here. Okay, so these all things are explained. Hence, the rule is when the two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multiple. Okay, so as we already know, delta z by z, as we already explained, when you're trying to understand absolute error, relative error, etc. What was relative error basically? The relative error is nothing but, right? So this is how this is similar terminology. See, it's delta z by z. Okay, therefore, when two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multiples. Okay, so this thing which is mathematically has been explained theoretically. Let's move on. Okay, let us try to implement this in the result here. Okay, so the resistance R is equal to V upon I. Okay, so this is one of these simple examples of your current electricity, that R is equal to V upon I. R is your resistance, V is your voltage difference, and I is the current passing through. Okay, they are giving the voltage as equal to 100 plus minus 5 volts. They are giving the value of current as equal to 10 plus minus 0.2 amperes. They are asking us to find out the value of percentage error in R. Please remember, it is percentage error in R. Okay, so total percentage error in R, how can we calculate it? So first of all, we need to calculate the value of so basically percentage error in R, as you already know, that delta R by R is nothing but equal to delta P by V plus delta I by I, right? This thing multiplied by 100 is being asked. If we just multiply this by 100, we'll get the answer. Okay. So delta V is nothing but 5 upon 100 plus 0.2 by 10 into 100. If I just do some mathematics here, you will get 5 by 100 into 100 plus 0.2 by 10 into 100. So this gets cancelled, this gets cancelled. Then we will get the answer as 5 plus 2, which is equal to 7. 7% is the answer. That is the percentage error observed in this complete concept. Okay. So the total error in R is nothing but equal to 7%. Okay. Let's move on. Okay, our little typical question now. So only things are being added, the concept remains the same. When you are trying to find out the error in sum or difference, then it will be nothing but delta Z is equal to delta F plus delta B. Yeah, it is always maximum relative error. Okay. And similarly, if you need to find out for difference, it is again delta Z is equal to delta F plus delta B. In the case of your product and division, you will do delta Z by Z is equal to delta A by A plus delta B by B. That is the maximum relative error. Okay. So let's look over to this question now. So the question states that there are two resistors of resistances. R1 is equal to 100 plus minus 3 ohms and R2 is equal to 200 plus minus 4 ohms. Okay. Next thing is which are connected in first of all in series, second in parallel. Okay, so we should always remember first of all just a brief explanation. So when the resistors are in series, then R equivalent is nothing but equal to R1 plus R2, and when they are in parallel, then R equivalent is equal to R1 plus R2 upon R1 R2. Right, let's move on. It's just a simple theoretical concept only. Okay, next thing is that find the equivalent resistance of the series combination and the parallel combination. They also give you the relation also. So for first, use the relation R dash is equal to R1 plus R2, and for second, use 1 by R dash is equal to 1 by R1 plus 1 by R2, and another concept also they give. Okay, so now let us try to find out the what is the basic thing as you need to find out the equivalent resistance. So equivalent resistance for the initial portion, which is not a tolerance, which is the value which is already provided, we'll just add. So simple addition, simple multiplication will be realized here. The main thing which we need to adopt is basically how to solve this or how to add up these concepts for your what we can say tolerance values, error values. Okay, so let's start with the first concept here. Okay, so let me just don't let me just keep on writing also. It's nothing but R1 plus R2. Okay, so R1 is nothing but your 100 plus minus 3 plus R2 is 200 plus minus 4. So 100 plus 200 will give you 300, and we need to find out the maximum value, which will give you plus minus 7. So this is basically the value of the equivalent resistance for the series combination. Okay, so now let us try to find out for the parallel combination, right? So for parallel combination, what will happen is first of all, for finding out the accurate value, which 1 by R dash is equal to 1 by 100 plus 1 by 200. Okay, so this will be into 2, which will give you 3 by 200. Therefore, R dash will be nothing but equal to 200 by 3, which will give you 66.7. Okay, so this was the mathematical calculation. Now for the calculation of your delta R value, they already give you this concept, right? So basically this thing has been obtained using the differential calculus. So right now there is no requirement of going to differential calculus, even if you try to use the concept which is involved there also, which I just explained you in the previous section. How can we try to solve this? Okay, so let me just go with one discussion so that at least you know that you can solve this question even using the concept which you already explained, right? So finally the concept required is we need to find out a tolerance of these values, right? The word which I'm using, tolerance, is basically everything which is written as plus minus. That error uncertainties, I am just writing saying that as tolerance values. Okay. So how can we do is, if we know the value of R1, we have the uncertainty of R1, we have the uncertainty of R2 also, right? So how can the uncertainty be set for the above portion? It is nothing but your 3 plus 4, which is 7. Okay. Now similarly we have some value of above portion, which is nothing but equal to your it is 300 plus minus 7 ohms. Okay. Okay, fine. Now for the below portion, what we can do is, we can understand this as a product of multiplication, right? Let us say there is some quantity Z which is equal to R1, R2, right? Therefore, what we can say is delta Z by Z is nothing but equal to delta R by R1 plus delta R by R, delta R1 by delta R2 by R2, right? From this calculation, we can obtain the value. So now what will be Z, what will be R1? So let us try to calculate. So delta Z by Z. Z will be nothing but 2 into 10 to the power 4. It will be 2 into 10 to the power 4, which is equal to, what is delta R1? Delta R1 is 3 by 100 plus delta R2 will be nothing but 4 by 200. So from this calculation, you can obtain the value of delta Z. है ना? So that delta Z would be put up here, and R1, R2 would be put up here, which is 2 into 10 to the power 4. Now you can just simply do the calculation for the, I think this will be opposite. Okay, sorry for my mistake. This will be inverse. Okay, so it's R1, R2 upon R1 plus R2, because it's 1 by R equivalent now, right? So 1 by R1 plus 1 by R2. So it's R equivalent to R1, R2 and R1 plus R2. Okay, I just wrote it as opposite thing. Right, so now what we can do is, so concept remains same only. So now we have this written here. Okay, so let me just change it. So it is this. Now you can write this as equal to 2 into 10 to the power 4 plus minus delta Z upon 300 plus minus delta 7. Right, you know this delta Z value also. Now just understand this concept as nothing but Z dash is equal to A by B. You have the condition for this, you have the uncertainty for this, you have the uncertainty for this. Let's try to do again this concept, delta Z dash by Z dash is equal to delta A by A plus delta B by B, and you will finally get the value of delta Z dash. Okay, so don't even look at, you need to memorize these formulas also. Even using the basic concepts also, these questions can be solved. Okay, sorry for that mistake. So basically Z equivalent for the parallel is nothing but, sorry, not Z equivalent, it's R equivalent. So R equivalent is nothing but equal to R1, R2 upon R1 plus R2. Okay, that was the basic concept. Fine, let's move on. So right now we can use directly this concept only. So we have the value of R dash. Now for this thing, we can obtain delta R dash. So R dash is known, R1 is delta R1 is known, R1 is known, delta R2 is known, R2 is known. Just put every value, you will get delta R dash is nothing but 1 volt. Therefore, the equivalent resistance of the parallel combination is nothing but equal to R equivalent, which is equal to nothing but 66.7 plus minus 1.8. Oops. Okay, the uncertainty for the series is very, very high as compared to the uncertainty for the parallel combination. Okay, just an observation, nothing coincident with it. Okay, fine. So here delta R is expressed as 1.8 instead of 2 to keep it conformity with the rules of significant figures. What are these rules of significant figures will be explained in the subsequent slides. But for now, just let us start understand at that point only. Let us understand this as part of fact only for now, that what we are doing, we are expressing the value of delta R as 1.8 instead of 2 to keep in conformity with the rules of significant figures. Okay. Now, error in case of a measured quantity raised to a power. Okay, so that concept is completed. So till now we have completed two different concepts. The first concept was based upon errors in your sums and differences. The second concept was based upon errors in product and division. The next concept is now based upon, then we did an example for both of those, I guess, for both of them. For both some difference product and basically two concepts which you already explained. Now let us move on to the next concept, that is error in case of a measured quantity raised to a power. What happens now? Okay, so as you can see, Z, let us say that Z is nothing but equal to A square, right? So what we can write it here? Okay, so one way can be using the differential calculus, right? So using differential calculus, it is directly delta z by z is nothing but equal to 2 delta e by e. Okay, so there is nothing to be explained here, but we can understand this as another way also. Let us say we don't know differential calculus. So what we will do, we'll write this z is nothing but equal to a multiplied by a. We already know that for z is equal to a into b, what is the significant thing? It is nothing but delta z by z is equal to delta a by a plus delta b by b. If we apply same concept here, it will be delta z by z equal to delta a by a plus delta b by b. Here delta b and delta b can be changed with delta a and a. So therefore, delta z by z is nothing but equal to 2 delta a by a. Okay. So that thing is only been done here. So they just did this thing and they finally got the result as delta z by z is equal to 2 delta a by a. Hence, the relative error in a square, this is a square basically, sorry for the error, is 2 times the error in a. Okay, so it's 2 times the error in a. So whatever will be the error in a, the error in that will be 2 times. Let us say the uncertainty is, let's say 2%, then the amount of uncertainty in z will be 4%. Okay. Now let us generalize this. Let us increase the complexity in this. If we increase the complexity, let us find that if let us say z is equal to nothing but a to the power b, p to the power q upon c to the power r. We're going to solve this. We're going to solve it. Let's say a is multiplied p times, and b is multiplied with it q times upon c multiplied r times, right? Or just solve. If you can apply a little bit of your experience, then you can finally find that delta z by z is nothing but p delta a by. So basically every power is being utilized. Okay, these all things are very easy if we understand the differential calculus concepts, but as this is class 11th introduction, so there may be a small time of stipular time is required to make you understand differentiation, integration, etc. Do not be hesitant with these concepts. It's very easy. Just keep on practicing everything and you will get to know differential calculus also very much easily. You can also refer to the appendix of your notebook, of your books, for finding out the differential calculus. The basic minimum amount which is required for physics can be understood or can be found in the appendix of these NCERT books also. Okay. Fine then. So let us understand this. So therefore, then delta z by z is nothing but equal to del p delta a by a plus q delta b by b plus r delta c by c. Okay. Hence, the rule that the relative error in a physical quantity raised to the power k is nothing but k times the relative error in an individual quantity. Okay. So hence, this is one of the final. Let's move on. Let us try to solve this example and then let us try. Yeah, okay, fine. So let us do these 2 examples and then we can close this lecture, and then next lecture we can directly start with significant figure. Significant figure is an important topic, maybe a tricky to understand, but only if you understand this decimal place very quite evidently, then the complete concept is very easy. Okay. Let's start. So find the relative error in z if z is nothing but 4 into b to the power 1 by 3, z to a to the power 4, b to the power 1 by 3 upon c into d to the power 3 by 2. So let's try to solve it on your own and then you can match the result. Okay, so it's easy only, nothing typical here. B to the power 1 by 3, then it's c, so okay, upon c into d to the power 3 by 2. Okay, so how to solve this? So it's delta z by z. So first of all, power is 4, so it's 4 delta a by a plus 1 by 3 delta b by b. Again plus, please remember it's not minus for a division, right? So it's 1 multiplied by delta c by c plus again 3 by 2 delta d by d. Okay, so it doesn't depend on its plus, minus, etc. And basically in multiplication and division, it's always plus. Okay, so therefore the final relative error is nothing but equal to 4 delta a by a plus 1 by 3 delta b by b plus 1 times delta c by c plus 3 by 2 times delta d by d. Fine. Let's move on to the next concept, final example. So the period of oscillation of a simple pendulum is 2 pi under root L by g. Okay, so if when you will understand the concept of circular motion also, this thing will be again derived. for now, even you can just remember this, that the time period of a oscillation of a simple pendulum is nothing but 2 pi under root L by G. Right? So what is here L, what is here G? So pi is already known to you. Pi is the value 3.14 basically. T is the time period here. Length is the length of the pendulum. And G is basically the gravitational force acting on it. Okay. Okay, so that is the formula given to you. Now, the measured value of L is 20 centimeters. Sorry. So L is given to you as 20 centimeters. The value of, and known to plus, okay, plus minus 0.1 centimeter. Plus minus, okay, let me just write it carefully. So length is given to you as 20 plus minus 0.1 centimeters. Okay. And 1 mm to 1 mm accuracy, and time for oscillation of the pendulum is found to be 90 seconds. So time is given as 90 seconds using a wristwatch of 1 second resolution. So basically the uncertainty in the time period will be 1 second, because that is the maximum least count, right? So if the resolution is given, then that is considered as the least count or the uncertainty which a wristwatch or which a basically a time measuring instrument can provide, or it has. Okay, so finally we just need to ask, or we just need to find what is the accuracy and determination of G. Okay, so just whenever such questions come in which there's a formula being involved, one of the suggestion is that try to solve this in terms of in terms of keeping all the things at one side and finding out the value of the required quantity. So whatever I'm saying is, so let us say for this example, try to put the value of G towards left hand side and try to find out the value of every parameter which is linked up to it. Okay, so as T is nothing but equal to 2 pi under root L by G, multiply both quantities, square both sides, so we will get 4 pi square into L by G. Therefore, what is G? G is nothing but equal to 4 pi square into L by T square. Okay, so if you see it clearly, then here G is nothing but a function of L and inversely proportional square of time. Okay, so what you can do, you can just find the uncertainty related to this part here. So because there is no uncertainty related to 4 pi square, right? So it's nothing but delta G by G is equal to delta L by L plus, please remember plus, because it's division and it's square T into T. So it's 2 times delta T by T. Simple concept here involved. So now how we will do, what we need to find? We need to find out the determination, accuracy. The percentage error it has, just multiply this value by 100. Therefore, this value can also be multiplied by 100. Therefore, final thing is, what we require is 100. What is delta L? Delta L is given to you as 0.1. What is the value of L? L is given to you as 20 plus 2 times delta T. Delta T is given to you as 1, and the value of T is given to you as 90 seconds. Okay, just put everything. Finally, you will get the answer as equal to 3. So that is the basic concept. That is the basic crux of this final exam. Okay, so let me stop everything, stop this lecture here only, because then new thing has to be started. Let us start that lecture, see subtopic fresh only. Okay, so next concept will be on significant figures, and then we can move on with the further concepts. Okay, fine. So course progress for you for now. So we started with introduction, then we understood the SI units, so basically the derived units and fundamental units, base units will be explained. Please remember there are 7 basic units of your SI system. Then next thing was measurement of length, in which we understood parallax method, and another was just theoretical portion in which we understood what is being done for the measurement of small distances, very small distances. The next thing was measurement of mass. One atomic mass unit was also been explained here. Then measurement of time. Next thing was about accuracy, precision of instrument and errors in measurement, in which I understood basically today was the basic discussion about the 6th point only. In the last lecture, we understood 3 basic concepts. One was your absolute error, then next was your relative error, then next was your percentage error. Today we also understood more about these all concepts only, and then we went on to understand combination of errors, as in what happens when we try to add some 2 different quantities and then find out the value of Z, what will be the error in Z. So it was been done for errors in some difference. Similarly, it was also done for errors in let us say product and division. Also, we try to understand that what will be the error when something has a power, some quantity has a power, let's say a square, or in more generalized term, let it be like a to the power x into b to the power y upon c to the power d. What happens then? So all those concepts have been explained, and that is the end of your sixth subtopic. Also, in the next lecture, we will go on with the significant figures, and then finally its dimension of physical quantities, and then dimensional formula and dimensional equations, and finally dimensional analysis application, and that will be the end of your units and measurements. Okay, so thank you so much for listening, and then we will meet in the next lecture. So thank you so much.